I'm in the process right now of preparing the solution for homework 1. I'm going to give that to the grader this evening, and I hope that he'll probably begin working on it over the weekend. So in general, I hope that your homework assignments will be graded within about a week time frame. So you submitted homework 1 on Wednesday. You should have it graded by about Wednesday of next week. My intention is to put the PDF of the solutions online so that you can take a look at your assignment, compare it to my solution, and that'll help you to learn and identify if there's any mistakes. So homework number 2 is due on Wednesday. I posted that yesterday. It's available now. Some of these problems are asking you to use the Colebrook equation, which you saw last time. I'm asking you to play around with the Jane equation, get some experience with that. And then it also goes a little bit further, talking about the pipe sizing and design example. So that's what we're going to talk about today. You remember that in class last time we went through this iterative process of knowing that there would be 45 meters of head loss as the water flows from the source pipe towards its destination. And with that known head loss and all the other physical parameters of the pipe, we found out what diameter would be required. But the tricky thing is that until you know the diameter, you don't know the flow velocity, and if you don't know the flow velocity, you don't know the friction factor. So we had to go through that guess, check, iterate process. And so as you work on your homework, I think it may be worth your while to review the lecture video from last time if you want a refresher on how to go through the spreadsheet and start with an initial guess and gradually converge towards the correct F value. So this is the accurate way to do that pipe diameter sizing. But it's iterative. What's not as accurate, and what's in theory you could say it's easier because it's not iterative, is to use this empirical equation. Now it's not valid for the same range of values as the other approach is, because what they've done here is they've kind of built in elements of the Jane equation to estimate the F value so that you don't have to guess. And so it's based on the pipe equivalent sand roughness, the pipe length, the flow rate, the expected energy loss. You can see kinematic viscosity is in there. And so it's kind of a strange equation. Let me just show you. We're not actually going to work an example to illustrate it, but I'll show you what the calculations would look like for this same problem. You've seen the spreadsheet version of what diameter is required. So if we were going to do that by the calculation method, putting it into that big, hairy empirical equation, then by the way, let's just remind ourselves what was the diameter it calculated. When we did it according to the spreadsheet method, it said that the diameter that we'd need in iteration, a diameter of 0.1707 meters. So that's the exact pipe size that would be required. Now if we do that by the non-iterative approach, so that explicit equation, then it's saying 0.175. So that's pretty close to the 0.171 meters that we got through the iterative approach. And so in the homework assignment, I ask you to use the iterative method just because I think that that's more valuable to get practice. The idea of begin with the guess and then refine that guess is an important technique that we'll use a lot this semester. So on the homework, you're going to get your first exposure to that with a problem that's similar to this one. But there is a direct way to solve for it. So any questions so far on pipe diameter sizing? Just to review, what have we been doing? We started the semester talking about, in theory, what causes flow resistance. We talked about the origins of pipe friction and why pressure decreases in the direction of flow when water's going in a pipe. And our empirical methods for estimating the magnitude of energy loss at the pinnacle of the pyramid, the most accurate and most widely used would be the Darcy-Weisbach equation. But the big disadvantage, of course, is that the F value depends on flow conditions, which a lot of times aren't known. So the Hazen-Williams equation, which you've seen before, last semester in fluid mechanics we did the lab experiment having to do with Hazen-Williams equation. Remember that it's not as valid for as wide a range of conditions. The pipe sizes are supposed to be between 50 millimeters and 1850 millimeters. So that should be a red flag right there. None of our pipes were that big last semester. So that's part of the reason why you didn't see the C values to be as consistent as they would have been if all of our diameters were in this calibrated range. Is the Hazen-Williams equation is intended mainly for the size of pipes that you'd see in a municipal water network, not tiny little pipes that you'd have in a lab. It's intended for water just at 16 Celsius. So you can still use the equation if the water is warmer or colder than that, but it's not going to be as accurate. And the reason why they have this fixed temperature is that it's not varying the kinematic viscosity of water. Hazen-Williams equation isn't accounting for a change in fluid properties that occurs as the temperature adjusts, whereas Darcy-Weisbach does take the temperature of the water into account, because when we calculate the F value, remember Reynolds number goes into that, and the Reynolds number accounts for the change in viscosity depending on whatever temperature it is. It's also intended for relatively slow-moving water. So Hazen-Williams equation has some limits, but a lot of what we do out in the field is inside those limits or close, and it's relatively easy to use. You've seen it in both the SI and the traditional units before, and depending on how we rearrange the equation, it can be used to solve for what the flow velocity will be if you have a certain S sub F. So remember, S sub F, the slope of the energy grade line, is defined as the change in head loss due to pipe friction divided by the pipe length. So if you know a pressure difference in some segment of pipe, you can use the delta P to calculate the H sub F, and then the H sub F per length, however far apart 2 points are that you measured the pressure, you'd take that into account to find the slope of the energy grade line. And so you can think of the slope of the energy grade line as the driving force that's pushing the water through the pipe. So if you have a lot of driving force pushing the water through the pipe, then you'll have a big velocity. And of course, the hydraulic radius for a circular pipe is what? Circular pipe flowing full.
D over 4.
D over 4. Good. And C sub H is the roughness coefficient that you can look up out of tables based on the material properties. So that's in terms of velocity. You can also express the Hazen-Williams equation if you don't know the energy loss, but you do know the flow velocity. So if you wanted to predict how low is the pressure going to be downstream for some measured flow conditions, if you know the flow rate and you're wanting to find out how much energy loss there is, then you'd use the bottom of these two equations. All right, so Hazen-Williams equation is very convenient, and it comes up a lot on exams you take to get licensed. You're going to take the FE exam, and you're much more likely to have a Hazen-Williams equation question on the FE than a Darcy. You probably won't have a Darcy equation on the FE. And so let's practice the Hazen-Williams equation, because they say the number one thing in education is you should teach to the test, right? That's a joke. They say you're not supposed to teach to the test. They say you're supposed to teach, to prepare people for the profession. And that's what we do most of the time, but I also want you to be prepared for the FE exam. So let's practice two different Hazen-Williams equation questions today. Let's practice this one where you're finding some unknown pressure downstream, where we want to find out at the spigot, here at the tap, where we know the elevation, and water's coming from some elevated tank that we're going to assume is open to the atmosphere. And the water's flowing at 11 liters per second, and so since we know the flow rate and the diameter, you can calculate the velocity with the continuity equation, V equals Q divided by A. So what I'd like you to do is use the energy equation and Hazen-Williams to predict what is going to be the pressure at this tap when we have 11 liters per second flowing through the pipe. All right, once we know the velocity, we can put it into the Hazen-Williams equation, which is estimating how much energy loss is there for that velocity. So Hazen-Williams equation says there's going to be 17.54 meters of head loss. And remember, head loss is just a way of expressing energy with units of length. So it's saying, you know, in the energy equation, there's the pressure head, elevation head, and velocity head. The energy can be in one of those three places. And as the water's flowing through that length of pipe, 760 meters of pipe length, 17.54 meters of head loss will occur. So now what we do is we take that H sub F and put it into the energy equation, because we know everything. In order to find P2, we know everything except for what was the head loss in the energy equation. So here's the energy equation. You can see that we cancel out P1 because we're talking about a reservoir that's open to the atmosphere. Cancel out the V1 term because it's a tank of water that's not moving. And I canceled out the V2 term. I guess you could debate on leaving it in because the water's maybe still moving as it goes through the spigot, but it doesn't end up having much of an effect. I accidentally crossed out the P2 term. I shouldn't have done that. All right. So did anybody finish the calculations and find that the pressure at location 2 should be about 303 kilopascals?
I don't know. I have like up to exactly the same numbers.
So look at the elevation difference is from 103.5 to 55. So let's see if that's right. So 103.5 and 55. So that's rearranging energy equation to solve for P2. Question?
Is it okay if I did keep the V2?
Yes. In fact, you did better than me if you keep V2 in, because that's more accurate, right? So what's the pressure if you leave V2 in? 301?
I got 302.
302? So what we're talking about...
1.5.
Okay, so we're talking 1 kilopascal out of 300 is the difference if you keep the velocity head versus take it out. So I think you're probably getting a sense for why often we just ignore the effect of velocity head, is that if unless the water's really moving fast, there's just not that much energy tied up in the velocity head. But if you left it in, good for you. That's even more accurate. Are there other questions on this problem? Could we have solved this problem with Darcy-Weisbach? Of course. So how would things have been different if this was a Darcy-Weisbach problem? Well, instead of a C sub H, you would have had to gone to chapter 10. I think there's a table in chapter 10 that tells you what is the epsilon for cast iron. So you would have gone through the process of maybe with the Jane equation, find out what is the friction factor, F, and it would just would have been a different equation that you're using to find H sub F. But then all the other parts of the problem would have been the same. You still would have had the same thing to find V. That didn't change depending on if you use Hazen-Williams or Darcy-Weisbach. And then once you have H sub F estimated, it would have been the same substituting it into the energy equation. The energy equation isn't different. It's just a different model for estimating the effects of pipe friction. So we could solve the same problem with Darcy-Weisbach. Okay, Let's take a look at this next Hazen-Williams equation where we find the flow rate.
Well, it's just a calculator issue. I have all the exact numbers, but when I crunch it in, it's not enough. It's just me.
All right.
Oh,
You've got it written out correctly then?
Yeah.
All right.
Thank you, though.
Sure.
I'm just frustrated at my calculator issue.
Okay, so for this one, we don't know the flow rate. V is unknown. So this is one where it would be trickier to do with Darcy-Weisbach. This would be hard because if you don't know the V, then you can't calculate the F. So this is one where we're kind of breathing a sigh of relief that it's a Hazen-Williams equation and not a Darcy-Weisbach, because it means we're not going to have to iterate where we would have if it had been a Darcy-Weisbach problem. But it's the same kind of process where we want to find out the slope of the energy grade line, S sub F. Now earlier today I told you what S sub F is. It's H sub F divided by L. So the H sub F is going to be the elevation difference between the two. Okay, so what does Hazen-Williams tell us about this one? The water. So the hard part here is knowing how to get the H sub F. You know, it's maybe the theory. It's not, the hard thing isn't putting the numbers into the equation or punching the numbers into your calculator, but it's looking at a picture and knowing that the elevation difference is the H sub F. I wrote it on the board. I said H sub F is delta Z, but why? Why is the delta Z the head loss due to pipe friction? Jeffrey?
Is it because it's the closed network in a way?
Okay, that's not wrong.
Is that the only way we're losing is that the only way we're losing head, just because the velocity?
Yeah, we are losing head. I guess the way that I would put it is, all right, look at the energy equation. So compare location 1 and location 2. So we've got no pressure at the tank, so P1 is 0. How much energy is there at 1? It's the elevation head. There's no velocity at 1. There's no pump here. Now at 2, once the water comes out of the spigot, so it's in contact with the atmosphere, it doesn't have any pressure. So we cancel out the P2 term. It does have some elevation, so the Z2 is known. Now the V2 term, we could put it in there or we could eliminate it. What I did when I said that H sub F is equal to delta Z, I was assuming that the velocity head at 2 is negligible. But you know, the way that we found the H sub F is you're solving the energy equation for H sub F. So you basically plug all the given information, and the only thing we didn't know in the energy equation was H sub F. So you solve for that and then put it into the equation. Okay, and then here's the calculations for that. Yeah, this is the one. Okay, should be 0.0192 cubic meters per second, so 19.2 liters per second. Did everybody else get this same velocity of about 2.4 meters per second? So the elevation difference is what's driving the flow through the pipe. What if the tank starts to empty? So right now the water elevation in the tank is 103.5. What happens when the water elevation gets a little bit lower? How is that going to affect our flow velocity? It's going to go slower. How come?
There's less force pushing it through the pipe.
Less force pushing it through the pipe. There's less energy at 1. As the water level gets lower, the energy at 1 to overcome the resistance is decreasing, and so that's why the velocity would be lower. Is S sub F is smaller if the elevation at 1 is less. So this is assuming like right now when the elevation is as described. But over time, when conditions aren't steady, that velocity might decrease. There are some other equations besides Hazen-Williams and the Darcy-Weisbach equation. I've referred a couple times to the Manning's equation, especially for those of you who are in the hydrology class. What Manning's equation does is it assigns a roughness coefficient that's called N, and it's often used in open channel flow, but in a pinch you could apply it in closed conduit flow. It's really not very accurate in pressurized flow. Manning's equation is really best for a flow that isn't pressurized, like a river or a creek or water going through a sewer pipe that's only partly full. So all of those are examples of open channel flow. But Manning's equation is really easy. In the same way that we had a formula with Hazen-Williams that estimates the velocity based on a roughness factor, some geometric parameters describing like the pipe diameter, for example, and then the driving force. That's what went into Hazen-Williams equation. Manning's equation is similar. It's got a roughness term. It has a geometry term that's describing the shape and the size of the channel that the flow is going through. And then it has an energy term, so like the driving force, what's pushing the flow through there. So there's some similarities, and there's a difference in units between SI and the British gravitational units. This correction factor of 1.485 is used when we're working in BG units. This is trapezoidal geometry, where in a trapezoidal channel there's some bottom width, a top width, and a series of equations we can use to find out what's the wetted perimeter and the cross-sectional area, because we can't just use d divided by 4 for something like this. In a circular pipe that's flowing full, the hydraulic radius is the diameter divided by 4, but in a trapezoidal channel or a rectangular channel, you're not going to use that same equation. So you'd actually have to use area divided by wetted perimeter to find the hydraulic radius. You also couldn't use d divided by 4 here. This is a sewer pipe, whether it's a sanitary sewer or a storm sewer. Those pipes are not designed to be pressurized. When they are, bad things can happen. A sewer pipe is intended to be partly full. And so to find the wetted perimeter, you would find this distance, and the cross-sectional area is just referring to the cross-sectional area of flow, not the cross-sectional area of the pipe. And so the geometry of a circular pipe that's partially full is actually really complicated. We won't get into that until the very end of the course, because that's the part of the course where we're talking about open channel flow, for one thing. But the geometry implications are a little bit tricky. It comes down to the angle that the water surface makes with the center of the pipe. But for now, since we're talking about different empirical friction loss equations, I wanted to draw your attention to there is something called Manning's equation, and we are later in the semester going to be using this instead of Hazen-Williams or Darcy-Weisbach. Hazen-Williams and Darcy-Weisbach really are limited to closed conduit flow. All right, 3:48, class is over, you get your time back. I forgot. Oh, now it says 3:49. Good thing I ended class right at the exact moment. Oof, that was a close one. No, I think I